Good afternoon, Professor. I'm Pradeep Thapa and I'm representing Team Uno. In this video journal, we'll present about our project 2, which is freestyle object tracking using OpenCV APIs. In this video journal, we'll present about our team members and their contributions, brainstorming session, brief introduction of object tracking, and comparison between different types of object tracker. We'll also discuss why we choose Kalman filter, description of Kalman filter, and finally coding explanation and implementation of Kalman filter. So we are 4 members in our group. Akash Khimire, he's our team leader. Vijay Prayar, Kesav Adhikari, and me, Pradeep Thapa. Firstly, to choose one algorithm from plenty of OpenCV APIs, all of the team members of our group had a brainstorming session. And in this session, we discuss about different types of object tracker. For example, Gotron, CSRT, TLD, Kalman filter, median flow tracker, etc. We did research on advantages and limitation of this object tracker, and we concluded that we will choose Kalman filter for this project. Now, I will talk about our team members and their respective contributions. Akash Khimire, he is our team leader and he handled our project. Vijay Pariyar, he did research and data collection in this project. Kesav Adhikari, he is our devil advocate and quality control of project. And I did the role of decision making and facilitator throughout the project. Now I'll give brief introduction about object tracker. Object tracking is is a process of estimating or predicting the position and other relevant information of moving object in a video. The tracking procedure can be viewed as a combination of two models. The first one is motion model. It tracks the speed and direction of the object movement, allowing it to forecast the object's new position based on received data. And the second one is appearance model. It is responsible for verifying whether the object we have chosen is within the frame or not. Now, our team member Kesav Adhikari will continue from here.
Hello, it's me Kesav, one of the members of the Team Uno. I am acting as a devil's advocate and quality controller of the project. During the research period of these projects, we came up with a different kind of algorithms or filters that are available in the field of object tracking. So I'm going to mention some of them with your advantage as well as the disadvantages. So firstly, discriminative correlation filters with channel and spatial reliability, that is CSRT filter, which works by training a correlations filter, and it shows comparatively better accuracy and resistance to the overlapping by other objects. However, it has a sufficiently low speed and also unstable when the object is lost. Similarly, generic object tracking using regressions network, GOTRON, is deep learning based offline tracking algorithms, which is good resistance to the noise and obstruction. On the other hand, when the first track object's speed is high, it loses an object. Talking about the learning detections tracker, TLD, which is real-time algorithms for tracking of unknown objects in the video streams, shows relatively good results in terms of resistance to the object overlapping by other objects. However, it shows like unpredictable behaviors in most of the cases. So request candidate method based median flow tracker is also shows sufficiently high speed and accuracy, but similar to the TLD, it is unable to continue tracking after the loss of objects. Moreover, Kalman filters a modern worldwide filter and which uses series of measurement observed over time. This filter is also applied in our projects, and further explanation in details of this filter will be given by our next team member.
Hello, everybody. This is BJ Parrier, and my ID is 12194945. I'm working as a researcher for my group, and my job is to collect various data according to the research. So basically, the Kalman filter is an iterative mathematical process that uses a set of equations and calculations uh, with in terms of data inputs. So we get data inputs, we use the equation and we perform the calculation, and we get the new estimation, and we perform another calculation and we get the new estimation, and so on. Unless the estimation uh, or the true value, we get closer to the true value. For example, let's say a car is moving from position A to position B. The car has sensors that determines the position of objects, as well as a model that predicts their future positions. But to be practical in real world, the predictive models and sensors aren't perfect. There is always some errors, or to be more generic, some uncertainties. So as in various weather change can affect the incoming sensory data. So the car cannot completely rely or trust on the information. So in these scenarios, what can we do to make the predictions more better? Or which kind of tracking technologies or algorithms we can use for the estimation? The answer is with Kalman filters, as we can mitigate the uncertainty by combining the information we do have with a distribution that we feel more confident in. It does this by combining a noisy measurement from a sensor with a flawed prediction from a process model. If the measurement noise can be modeled as a Gaussian distribution, then a linear Kalman filter will produce an optimal estimation. The optimal estimation is the product of two Gaussian distributions. So we could say linear Kalman filter equation can be thought of as a prediction step plus Gaussian multiplication. As Kalman filter is one of the popular tracking algorithm, some of the real-time application examples of Kalman filters are determination of planet orbit parameters from limited Earth observations, tracking targets, as in aircraft, missiles, using radar technologies, and robot localization and map building from range sensors, and many other computer vision applications, for example, future tracking, fusing data from radar, laser scanner, etc. Being the most versatile and better predictive model for tracking objects, Kalman filter suffers with various problems, as it is very difficult to compute the covariance matrix of noise of various sensors and systems. And the filter needs to process several samples in order to get enough iterations to produce meaningful results, which means it consumes a little bit more time. And the further explanation of a Kalman filter and the description of our product will be given by my fellow teammate and the leader of our project, Akash Kumire.
Uh,
Thank you, Vijay, for your explanation on Kalman filter. As you have described some of the path of Kalman filter as well as the problem and its usefulness, now I'll shortly talk about some of the mathematical concept. So first, we have this state matrix. So state matrix are useful, are also known as transitional matrix. So what it does is, like during prediction, it uses the previous time frame values such as speed or its position to predict new position and new velocity. To do so, it actually uses simple kinematics rules which we have been learning during our high school or first year of engineering. But we have this one more term, WT, which we did not learn during our physics. So WT stands for those noise uncertainty which can occur in real life. For example, the road cannot be as smooth, so there is always chance there will be the velocity may not be similar, and there can be many bombs and the wind condition. Uh, Many things can affect the rules of kinematics, and this there is always chance of uncertainty. So let's look at what this X matrix looks like. Under the X matrix, we have four variables, namely x, y dot x dot y. X is the location in x direction, similar y is location in y direction, and x and dot y are their respective velocity. So what now in the below formula we see those terms which we have already learned in our high school. So for this I'll not go into very depth because this video cannot should not cover this part. So but in simply what this does is it is used to predict the new location x. We are using the initial location multiply added with uh, velocity multiplied with time, and plus half of acceleration multiply square of time. So in here we see this A and B. So A and V is a simple because X is also in matrix formula. We cannot use we are using the same thing described in here but with the help of matrix. Now the working cycle of Kalman filter. So we have this initial state. So initial state or in the state matrix, the variables come from predictive model. But if we think during the first time when the value is just measured, there will not be any prediction. So what do we do at that time? So I will explain that term using this block because this was one of the simplest uh, definition I have found. So in the first, what we do is because there is no initial state, we will initialize those initial state x and y with the value we get from measurement itself or the bounding box. In our condition, is the bounding box of the object to be detected, and y and m. But still, there is no velocity to be found because velocity is just x2 minus x1 with delta t. So we'll again reinitialize those terms, and after that we'll have this X matrix. Now again coming back to the presentation slide. So now we have initial state. So these are the state. So P covers stand for the noise matrix, or simply it related to WT matrix, which we have seen in the before slides. Now, using those previous state, we can predict this initial state become the previous state, and we can predict the new state, coming state, using those simple kinematic rules. But we are also accounting the noise. Now, this predicted rule can always have this uncertainty, and to cover that uncertainty, we can take advantage of measurement device. Why? But there is also uncertainty within that from that device itself. For example, in our case, we'll be detecting bounding, we'll be detecting some object, but what if the detection of the object itself is not that good? And then there will be always that error. So we'll only look at the important terminology within this Kalman gain. So which is also one of the important terminology within the Kalman filter itself. So we can see here PT, which accounts for this error comes from the prediction model, and R accounts for prediction comes from the uh, measurement. So okay, now we have understand this. I'll go into new slide, where will again talk about Kalman filter, but in a very simple way. So Kalman filter is more likely the ratio of error comes from the estimation to the ratio of error, which the summation of estimation and measurement. So if we observe that if the estimation error is wrong, then that means that the predictive model is estimation error is 0, then that means that predictive model is very correct. In that sense, this is very correct. Then we don't need to update that value. So it becomes 0, and this value comes from the predictive model only. But in the same sense, if measurement value error in the measurement is 0, then we highly depend on this measurement value P, which will be updated to the previous value. So in this way, Kalman filter is accounting the error for coming from both prediction model as well as measurement model. Now we have learned the fundamentals of how Kalman filter works. Now let's go into the coding. Okay. In the coding part, because Kalman filtering is a two-step mechanism. Firstly, we have to detect an object. After that, only after finding the sent route, then only the tracking can occur. So firstly, we will define the for object detection. So for the reference, I have taken help from PySource. Here he have also used very simple object detector based on the color itself. So what this do is like, firstly, if you see, it takes the input frame, and the input is an uh, BGR BGR image. So when it takes that input, so we want to convert into HSV format. Why? Because HSV format are considered better when we take account for color specification. So after that, we calculate the marks by defining the low range and high range. So we have this HSP color into two different range, and if within that frame some object is uh, in that value, between that value, we will create a marks. But in an object there can be many marks. So which marks to use? So which counter to use? To do that, we sort this, and after sorting, so there is also one argument, this MOD, which is a multiple object detection. So if we are not only doing for single object detection, what we do is only takes like single object. But if we are accounting for many objects, we'll do that accordingly. For example, if I'm just doing single object detection, then I'll from the sorted value, I'll take the bounding box which has the biggest counter area. So now we have walked through with this object detection. Now let's go to the Kalman filter itself. So Kalman filter can be used with using OpenCV. So OpenCV has this method Kalman filter, which method class which takes two arguments mainly to initialize. These are the arguments of how many integer dynamics it has, and the total number of measurement parameters. So now for measurement parameter, which is the bounding box of the object detected or orange color detected, it will be only x, y. So there is only two value. But as the prediction model gives x, y, and dot x dot y, it has 4. This is the reason we are giving 4 to. So this kf dot transition matrix, nothing but A, which we have seen in state matrix. But to make it more simply, we can see this is representing the same thing. After this, it can give us new predicted x, y, and new predicted dot x and dot y. And this measurement matrix is a matrix accounting for x and y. So we have this 2:4 format, and for this we have 4:4. So now comes this predict method. So within it, first it takes the coordinate x and y from the object, that is detected object orange in this case, and after that it can do under the hood. What it does is it first predict the new dot x dot y, this 4 by 4 matrix, and they calculate the Kalman filter, Kalman gain accurately, and this correct function does is make it even better, like correct update using those Kalman gain. After that corrected, we'll predict a new value, uh, which will give new x and new y. So in this way, we will be tracking, not only tracking, but while we have object at timestamp t0, we can predict the new value as timestamp t1 and t2. Now let us walk through with coding. Now, first, for the walkthrough, we have these test videos. Under it, we have many videos like videos for multiple object tracking. So also what happens if there is occlusion, and at the end, we'll also do tracking from the tracking tracking live tracking as well. And okay, let's start multiple object tracking. So to walk through the code, it simply reads the video, and we have initialized the orange detector, and for now we have multiple object detection. We have set it to true, so we can detect 2 objects at a time. And so we have called the Kalman filter. Now it's time to run the code. So what it does is we can easily get the predicted values x and y. And we'll draw the original cx and cy with dot filled with red value, while we the predicted value will be blue and other will be more like gray. So here I have initialized I have initialized frame by frame. We can see there are two object, orange object. One is this 1 carat and 2 carat. So this red dot, you can see it is the it is the measured value from the object detection, and this is this calculated cent rate. In the first state, we can see this Kalman filter doesn't do a good job, because how Kalman filter progresses, as long when it gets more and more and more data, it becomes more and more stable. So when you go to second frame, okay, now it's improved little bit. Third, now we can see there is a lot of improvement. Fourth, in the fifth, we can see like there is a lot of improvement. So in this way, it is doing a good job, and we can see like this is even like successing when there is occlusion. Like we cannot see, we even with our human eye we cannot see the carrot, but there is still it predicted the new value. But okay, it now if you see it fails to re-identify, because this may be because this may be the problem, because we are using a very basic terminology, very basic Kalman filtering, and it's failed to reassociate it when it cannot detect the object itself. But still, it is doing very good job. We can see this the bigger circle is predicted, and the smaller circle is the real value, and it's doing very good job. If I run without any with delay of 10, okay, we'll see the full video. This is another one. So we can see it does very well. 100 maybe. Okay, this is a case where there is a case of occlusion. My friend is throwing the orange. Okay, let me show you the image by image to make it even more clear. So this is single object tracking, and I'll set it to 0 so we can see frame by frame evaluation. Okay, first thing is it doesn't. Okay, in this case, this bigger X is the original value, and this dot X is the predicted one. Blue is the predicted one. So prediction is not very good at the beginning. It's still not good. It becomes little bit coming closer. Now it is predicting the new step. This is the new step. It is predicting that at next frame or next time it will go here and it will follow some parabolic uh, path. Now you see as we fit more and more data to Kalman filter, the prediction and the original value are coming more and more closer. But what happens if there is occlusion? So now in this part, maybe this is because this detection is still Kalman filter is not doing very good job for re-identification when the object itself is lost. We can see some predicted value, but we cannot see the ball itself. So it is kind of failing when there is occlusion. But when the object again reappear, but this time it is again tracking. So I'll play the video. Okay. Now to test that, analyze that, we are also using graph. So I'll explain the graph. So this blue line detects the ground truth value, the path followed by the original center, while the orange path is the path followed by the predicted value. You can see like the first prediction, the prediction is not very good, but as the number of frame increases, the prediction becomes as close as the prediction. And at this point from frame number like around 100 to 600, it actually overlaps, and there is very good prediction. Now we will also predict using a YouTube video we have found. Actually, this is also one of the reference we have taken. So if we use the real orange, as you can see, the prediction, this big red is very close to the original bounding box blue. It does very good thing like predicting. So Kalman filter is working perfectly in this scenario. And if you again analyze it, you see it follows a parabolic because the path was also parabola, but you can see the Kalman filter like doesn't take a lot of time. Now it's time to test on live video. One of the reason I'm not turning on the camera is because for the live video I have to turn on the camera using OpenCV, and when I am opening camera, then somehow Zoom is not able to zoom, and this OpenCV has some conflict. Okay, it's taking some time to. You can see the red. The bigger one is the like predicted value, and the original one, and it's tracking very well, very well. I'm moving very fast. I'm moving very fast. I'm doing this. This is detecting very well. So when I just put it in the frame, doesn't detect, but as the number of data increases, it predicts very well. It predicts very well. Okay. Now to analyze this again, there were like the motion was not like doesn't follow in particular path, so we don't have a specific curve, but what we can see is this predicted curve and like the ground truth curve is very very close. So we can see our model performs very well. And now we don't have a lot of time, so in conclusion what I'm going to add is, so yes, the Kalman filter that we are working doesn't work very accurately when we are working with like occlusion, but the main focus of this project was to get familiar with the tracking, and there was no other way to learn it better than using Kalman filter. Why? Because if we see like most of the SOTA like deep sort or pure MOT, Kalman filter is just a building track. So now we have learned this Kalman filter. Now it makes it very easy for us to like it not very easy, but it makes it us very comfortable to learn those short and deep sort or pure mode, which is the actual SOTA. So this will be helpful to all of us. And this is the end of our video channel. Yeah, it took a few more minutes to explain, but I'm sorry for that. Now I'm closing the session, and thank you for listening. Have a good time.